Hi, I'm Foteini, and today I'm going to present my project on testing the potential of machine learning, and in particular deep neural networks, for producing short-term data-driven spatiotemporal earthquake forecasts. So over the last years, we've seen quite rapid advancements in the field of machine learning, and this is because we now have a lot more data available than we did before, and also we have much more computational power available than we did even a few years before. So it does make sense to try and use the power of machine learning in the context of seismology as well. So there have been various studies that use machine learning to address problems within seismology. So there have been studies on using machine learning for Earth model inversions, but also tasks like seismic phase picking. So we have two deep learning based phase pickers that are quite widely used now, FazeNet and EQ Transformer. And also we've used machine learning for tasks such as event discrimination, phase association, source characterization, and stuff like that. So my project falls within the domain of predictive tasks within the field of seismology. And the main challenges in this domain are the use of existing data that we have available to reveal hidden connections and uncover new physical laws that we may not be aware of. The development of models that are able to account for the scarcity of large magnitude data, the development of reliable evaluation methods, and we also need to overcome the barrier of non-explainable prediction. So this is an issue pretty much in all fields where deep learning and machine learning is applied, because often one of the main problems with machine learning is that it usually acts as a black box. So we're not really able to understand why it's making the decisions that it's making. So the motivation behind this project is the fact that deep learning techniques have recently succeeded in producing very high resolution earthquake catalogs. So these catalogs contain a lot more events, so at least a factor of 10 more events compared to traditional catalogs. And they're created at significantly reduced processing times when compared to human analysts. And there have been studies that show that forecasts that are informed from these machine learning catalogs are more informative compared to forecasts that use traditional catalogs. So the idea behind this project was that we might as well try and use machine learning in order to uncover new relationships within earthquake catalogs and discover patterns within earthquake sequences. So here we see A is a standard catalog and B is a catalog that has been generated by machine learning. And the events that are plotted here are the events above the respective magnitude of completeness of each catalog. So we see that B, the catalog that has been generated with machine learning, contains a lot more events. And these are mostly small events that we weren't able to detect before. And so, yeah, it makes sense to try and use this new wealth of data that we have available to try and produce earthquake forecasts. So the data set that we use is a data set of earthquake catalogs, which we have assembled. So we have earthquake catalogs from different regions: California, southern and northern California, New Zealand, Japan, Italy, and Greece. So we're not using catalogs that have been generated with machine learning yet, because these are not available for many regions. So we have set a magnitude threshold of 2, because this is roughly the magnitude of completeness of the catalogs that we're using, and also a depth threshold at 40 kilometers. And so what we're doing with these catalogs is we're building these seismicity maps. So we have the rate, the magnitude, and the depth map, and we build these by gridding the spatial area that we have into bins of 0.1 longitude and latitude degrees. And then for the rate map, we count the number of events that we have in each grid cell per day. And the magnitude map has the maximum magnitude per grid cell per day. And the depth map, for depth map, we calculate the average depth of the events in each grid cell. And so we have these three maps, in which we have it, so they're essentially spatiotemporal sequences, because we have them for every day. And what we first tried doing was build forecasts for the whole region that its catalog covers. So we were interested in short-term forecasts, so we would try and build a forecast for the next day for the whole region of Southern California, for example, here. But this was a bit problematic because the maps that we have are very sparse. So even in this case here, where we have a day where quite a lot of seismicity is going on, and we have large magnitude events as well. These are quite localized, so in many regions there is nothing happening. So it's very hard to do something with data that are this sparse. So what we thought of doing instead was identifying large events, and so events with magnitude 4 and above, and create a grid around these events and sort of take the data in the same region for 7 days before and produce a rate forecast, so a rate map for the next day in the same localized region. So it is sort of, what we're doing is sort of like forecasting aftershocks of large events. And we do this using a neural network. So let me just briefly mention how neural networks work. So we have our input data, which in our case are 3 sequences, 3 spatiotemporal sequences, the rate maps, the magnitude maps, and the depth maps. And we have n of these sequences in the training set. So we pass these sequences through the neural network, and we produce the forecast, which is the rate map for the next day in the same region that the input data cover. Then we calculate the loss on the training set. So this is basically the error between the ground truth and the forecast that we're producing. And we do this using a function that we define. So here we've used a simple mean squared error function. And then once we do that, we have to update the network's weights by calculating the gradient of the loss function with respect to the weights of the network. And we do this iteratively until we minimize the loss as much as possible. The type of models that we use for this are called sequence-to-sequence models. And what they do is they learn to predict a target sequence from a source sequence, and they use an encoder-decoder type of architecture where we have an encoder which creates a representation of the input, and then the decoder uses this representation to produce the final target sequence from using what is created by the encoder. We use 2 types of neural networks for this. The first one is a convolutional neural network called UNIT, where you have the encoder part, which has convolutional layers that downsample the input. And then you have the encoder part, where you have convolutions that upsample again until you reach to the final target sequence. And you also have the skip connections. So you need to be connecting the respective encoder layers to the decoder layers in order to minimize the information that you lose due to downsampling. Because the final hidden state of the encoder is often not enough for the decoder to generate an accurate prediction. And so the second type of neural network that we're using is called a transformer. And this can be seen as, so the structure is pretty similar to the convolutional neural network, but instead of using convolutions, so fixed filters, we have filters that are learned as the network is trained. So the network sort of learns to which parts of the input are more relevant to produce the output. And so, yeah, this helps with keeping only the information that is relevant. Our workflow, so we get the catalogs. So we get all the catalogs, and in all the catalogs from all the regions, we identify all the magnitude 4 and above events. And then for these, we build these spatiotemporal sequences of rate, magnitude, and depth maps. And then we have a number of examples of these. And we randomly choose which examples would go into the training and the test set. And we do this because the quality of the catalog, so the magnitude of completeness, is not the same across all the time period that we're using. So we're using data from 1980 to 2023. And yeah, so recent data have a higher resolution. And so we thought it was a fair way to select randomly the examples that would go into a training and test set instead of using the older data set for training and the newer for testing. And then we pass these through. So we train the neural network, and then we use a test set to evaluate our performance. And so we trained a convolutional neural network, a unit, a transformer, and what we do is we compare the trained models with persistence, which is a baseline that is frequently used in forecasting. So it has been used in weather forecasting and other time series forecasting problems, which basically assumes that there is no change between consecutive time steps. So we would use the map of the day before as the next day's forecast, assuming that there will be no change, so without doing any calculations. And we use 3 versions of these. So we use the day before, we use the average of the previous 7 maps as the forecast, so the previous 7 days maps, and the random map of 100 days before. So here we have some results. So our problem is a regression problem because we're trying to predict continuous values. So we're trying to predict, to forecast the rates, so the number of events that are happening in each grid cell. And so we've calculated some metrics that are specific to regression, so the mean absolute error and the root mean squared error. But we also wanted to see whether we're predicting earthquakes in the correct locations. And so to do this, we calculated some metrics that are usually used for classification. And to do this, we converted the continuous maps to binary maps. So in the grid cells where we have predicted at least 1 event, we convert them to 1, and then the rest, the other ones where we have no events, then it's 0. So then we have 2 classes, and we calculate those classification metrics. So for example, precision shows the proportion of predicted positives that were actual positives. And then the recall also shows how many of the actual positives were predicted correctly. And so we also calculate the accuracy, which is generally shows how many of the observations were correctly classified. But in our case, this is not very helpful because our data set is quite imbalanced. So we have a lot of true negatives. So a lot of cases where we predict that there would be no earthquake and there really is no earthquake. So we have also calculated the critical success index, which shows, it is the same thing as accuracy basically, but without the true negatives. And also we have the false alarm ratio, which is a proportion of false alarms with respect to the total alarms that we are giving. And so it seems that persistence, especially the version that uses the day before's map, the map of the day before, as the forecast, is doing a pretty decent job, which is quite surprising given that it has no parameters and so it needs no calculations basically. But this is because the maps that we have are, the maps of the consecutive days are usually very correlated. So yeah, so this is why. And then about the trained models, they seem to both be doing quite well, and they perform quite similarly, but the unit needs significantly less training time compared to the transformer. So the unit needs around 4,000 seconds to train, whereas the transformer needs 65,000 seconds. Yeah, the unit would be preferred in this case. And here are some examples of forecasts we've produced. So on the top row, we have the ground truth. On the second one, we have the unit. The third one is the transformer. And then the last 3 rows are the persistence versions. And we see that both the neural networks seem to be doing pretty well and understanding the shape that the forecast should have quite well. But this one, the persistence that you used the day before, also does pretty decently. And so, as a conclusion, the first conclusion is, first of all, that persistence is very hard to beat. So it's taken us quite a long time to be able to train a network that does better than persistence. And yeah, this is quite interesting because persistence is a very simple model, but it nevertheless does very decently. And the 2 neural network architectures perform similarly, but the unit needs significantly less training time compared to the transformer. And so as future work, we want to incorporate metrics from the Collaboratory for the Study of Earthquake Predictability, which is a group that is developing metrics that are specific to evaluating the quality of earthquake forecasts. We want to train on catalogs that are generated by machine learning, quantify the uncertainty of the forecast. So the forecasts that we have now are deterministic, where we would like to maybe move to a more probabilistic sort of thing. We would like to work on explainability as well, and finally compare against disciplinary statistics and physics-based models to see how are we doing compared to those. So with that, thanks.